Hello everyone, welcome back. So now we're in example 2. Not quite as simple. This time we have to figure out what our internal bending moments are because we're now looking at it with this applied load of 6 kips at the center of this beam. So we have a 14-foot long simply supported timber beam. Carries that 6 kip concentrated load at mid-span. And what we want to find are quite a bit. First off, at section AA, so right there, we want to determine the magnitude of the shear stress in the beam at point H, which is right here. We also want to determine the magnitude of the shear stress in the beam at point K. We also want to know what the maximum horizontal shear stress that occurs in the beam at any location within that 14-foot span length, and also the maximum tension bending stress that occurs in the beam at any location within the 14-foot span length. So there's a lot there. But it won't be too terrible once we actually get through it together. So take a few minutes, try this on your own, look back at the equations we had in this section, and see if you can figure it out. If you can't, come on back and we'll do it together. So 3, 2, 1, and we're off. First off, let's get those section properties out of the way. Luckily for us, it's a simple timber beam, so the moment of inertia is simply base times the height cubed over 12, so 1,687.5 inches to the fourth. And then our shear stress at H, well, we're going to need to know some information at that point. First off, what is Q? What is Q? Well, Q is going to be the area above H times its centroid. So let's look back at this again. We're going to go jump back a few slides right here. This is H. So this is the area above H. It's got an area of 3 times 6. And the distance from the centroid, which is luckily for us right at the center of this beam, to that point is, okay, well I've got 7.5 to the top. And I come down 1.5 to get to the center of this beam because I'm going to go from here to here. That's my distance. So that's 1.5, that's 6. So my distance would be 6 in this case. That's Q. Now, how do we know that it was 3,000 for V? We didn't actually solve for that. That's simply because there's 6 kip load right here, which means that both of the reaction forces are 3,000. So at this point A, I would be feeling a 3,000 pound load, or 3,000 pound internal shear force because of my initial reaction force. Okay, jumping back forward. Oops, sorry, went too far. So with this, I can find the shear stress at H. That's not too hard. We showed how we got Q. Moment of inertia was already calculated, and we know what the thickness is, which is simply 6 inches. Now, what's the shear stress at point K? Well, it's not going to be too terribly bad. We have to figure out the area and then the distance to the centroid of that area. So it's the exact same thing we're doing here. We did before. This was slightly different choice. So I'll let you go and look at this and you can verify that this is correct. We have the same load, we have the same moment of inertia, and the same thickness. So with that, we can also see that this is going to be 12.44 psi. 12.44 psi. So we're doing pretty good so far. We have, I think, one more section to go, which is to say, what is the maximum shear stress at any location? Well, the max Q happens at the centroid. So if we have a rectangle, when half the area is above it, that is when you reach the area that's above the neutral axis, or the area below the neutral axis, that is when you have your max Q. So the max shear stress is always going to happen through the centroid. So that would be our shear force, which is 3,000 pounds, times our first moment of area, which is the max first moment area, so as much area as we can, over the moment of inertia times our thickness. It comes out to be 50 psi. 50 psi. So this is the big thing that you would have to have realized for that when we're trying to find it. But it's not too terrible. Not too terrible. So, last thing, what's our maximum bending stress at any particular location? Well, our maximum bending stress is going to be where we have our maximum bending moment. That's going to happen right at the center of my beam. And then the maximum normal bending stress would happen at the surface, so either the top or the bottom. So 7.5 inches, we're just choosing the top arbitrarily. And then we divide by our moment of inertia. Do not forget to convert. It gets really frustrating when you forget to convert and you can't figure out why is my problem wrong. It's because you forgot to convert. Happens to me. I am not above this, but it happens to everyone. So try your best there. And I think that's everything. So yes, it is. So thank you for listening, and I will see you all next time. Have a wonderful day. Bye-bye.